Hello and welcome to lesson number 10, Laws of Indices and Logarithms. So let's start off by first talking about what an index is. What are indices? So consider a to the power of b equal to c. Over here we're taking a to the power of b and then that result is equal to c. In here what a is what we call the base. Here a is what we call a base, and here b is what we call the index, and c is like the result or whatever you want to call that one. But here a is the base and b is the index. You already kind of know what this operation here is, but we have to start from the beginning in order to explain what it actually means. So let's start off by what we mean by, let's say, something like 2 squared. What we mean by 2 squared is when 2 or this power or index is an integer, what we mean is repeated multiplication. So in the case of 2 squared, what we mean by 2 squared is multiply 2 by itself 2 times. So this is 2 times 2. 2 times 2 is repeated addition. Multiplication is repeated addition. It's adding 2 to itself 2 times, which is just 4. If I say 2 cubed, what I mean here is, for integer powers it's very easy to understand. 2 cubed is just telling you to multiply 2 by itself 3 times. So we have to multiply 2 by itself 3 times. In doing that, now we have 2 times 2 times 2, which then gives us 4 times 2, which then gives us 8. If I do 3 squared, what I mean here is multiply 3 by itself 2 times. So we have 2 3's here, which means we then get 3 times 3, which is 9. So here, for integer indexes, it is very easy to understand what we mean by this thing where we're taking the power of one number to certain other number. In fact, let's explore for the first little bit only integer powers. So let's only consider integer powers. I'm going to label some things here. I'm going to say let a and b be elements of let's say the real numbers for now, and let's let we'll call them m and n. M and n be elements of the positive integers for now, inclusive of 0. We're going to allow 0. So let's try to figure out what we mean when we talk about indexes. Consider a to the m and also consider a to the n. What each of these means? Well, a to the m means we need to multiply a by itself m times. So we have a times a times a times, along we go, times a, and in total how many a's are there? Well, there's m a's here. In terms of a to the n, if we consider a to the n, this is a times dot dot dot, so many a's, a times a, and here we have n a's. So in the top, a to the m means we have m a's multiplied together, where m is a positive integer inclusive of 0, and n, a to the n, gives us n a's all multiplied together. So if we consider a to the m times a to the n, we can find our first index law. Right now we are very limited because we only have positive integers, but we can see for our very first index law, a to the m times a to the n would be a times dot dot dot, so many a's, m times all multiplied, whole thing here, multiplied by a times dot dot dot, all the way down, lot of a's. And how many a's are here? Well, there's n a's here. So we have m number of a's multiplied by n number of a's. In total, if we consider the number of a's we have here, there are m plus n a's in here. Now consider what a to the m plus n means. A to the m plus n is just multiplying a by dot 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 by a in total m plus n times. So here we can see a to the m times a to the n is equal to a to the m plus n. This is going to be our first index law. We're going to write it down. A to the m multiplied by a to the n is equal to a to the m plus n. This is true currently. This is true for all the values that we're going to consider. It is true for non-integer m and n as well, but right now we're only considering integer m and n. But no, this right here, a to the m times a to the n being equal to a to the m plus n, is true for non-integer m and n as well. But for now we're only considering integer m and n, so that our analogy of having m a's and n a's and then m plus n a's and all of that works nicely and is easy to demonstrate. But note, this rule works for when m and n are not integers as well. Next, let's try and consider what a to the m divided by a to the n is. A to the m divided by a to the n. Well, on top we have m a's in total. We have a times a times a times dot 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 times a times a. On top we have m a's. On bottom we have a times a times a times dot 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 times a times a. And here in the denominator we have n total a's. So let's consider two cases here. If m is greater than n, if m is greater than n, that means there are more a's on the top than a's on the bottom. Meaning we can cancel some of them out. If we start cancelling a's like this, we'll cancel a lot of a's, and we'll be left on top, we'll be left with a certain number of a's. If m is greater than n, it means that all the a's in the denominator can be cut, leaving some a's behind. How many a's are left behind? Well, if we write it out, this is equal to a times dot 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 bunch of a's. There are in total m minus n a's that survive this encounter, because we started cutting. For every a in the denominator, we cut an a in the numerator. If we cut n a's from the denominator, we must have cut n a's from the numerator. If m was greater than n, there are m minus n a's left. So in the case where m is greater than n, we have a to the m divided by a to the n is equal to a to the m minus n being easily visible. However, if n is greater than m or m is less than n, then we have that we are dividing by more n's than we have on the more a's than we have on the numerator. In this case, this is the case where m is greater than n. If we consider n greater than m, we have a to the m divided by a to the n being equal to a times dot 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 a bunch of a's times a times a. This became a little ugly because my pen slipped. I'll erase that and write it again. A times a dot 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 whole thing divided by a times bunch of a's times a times a. On the numerator we have m number of a's, on the denominator we have n number of a's. And here, if n is greater than m, what we have is all the a's on the numerator will be cut, and they'll be cut for m number of a's on the denominator. So we'll be left with 1 divided by a times a dot 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 times a total of n minus m number of times on the denominator. So what I want to show to you is that this is also equivalent to the above result that we found if we allow for ourselves to expand the definition of the index. Currently we only considered indexes of positive integers. We only considered this b being elements of the positive integers, but now we are going to have to expand our frontiers and consider this index being things other than positive integers as well. So for this thing, we are going to say that 1 divided by a is a to the negative 1, meaning that negative indexes are just 1 divided by the positive corresponding index. which then means that what we have here is a to the negative n minus m, i.e. what we have here is still a to the m minus n. So here we have expanded our definition of indexes. We don't no longer need to have positive indexes to make sense of it. Now we can have negative indexes as well. And now we have expanded to say that in this case as well, a to the m divided by a to the n is equal to a to the m minus n. So as a summary, for any m and n, we've only considered it for integer m's and n's, but now we can expand it to non-integers as well. We do not have that yet, but we know it is true for non-integers as well. I can prove that later, but for right now, m and n are integers, positive integers, and then a to the m divided by a to the n is equal to a to the m minus n, no matter if m is greater than n or less than n, because now we've expanded our definition of the index. If we have a negative index, it means we have to divide by the positive index corresponding to that. There's also another thing I want to talk about, the zero index. What does it mean to have a zero index? So we can think of it like this. Over here, from our division thing, we have that a to the m divided by a to the n is a to the m minus n. Consider a to the 0. A to the 0 can be written as a to the n minus n for some n. We just found what a to the n minus m minus n is, and that is a to the m divided by a to the n. So therefore we could also think of this as a to the n divided by a to the n. So here we have, as long as a is not 0, because if a is 0 we have a divide by 0 issue here. If a is not equal to 0, if a not equal to 0, then a to the 0 is the something divided by itself. Anything divided by itself is just 1. So here we have equal to 1. So therefore a to the 0 now has a meaning. A to the 0 is 1 provided that a is not equal to 0. If a is equal to 0, we can still sometimes consider it as 1. Sometimes some people will argue it's not equal to 1, and they are absolutely valid in that, because a to the 0 where a is 0 is like a divide by 0. So there's a small issue there. I'll show you a graph of what a to the x looks like for different x's, or I'll show you like what x to the x looks like for different x's, and you can see that as x approaches 0, it seems like the graph is going towards 1, but it doesn't actually exist at 1. For now, we have to consider that 0 to the 0 is undefined. We do not know what exactly 0 to 0 is. It is simply left blank and undefined. We do not have it. But for any other value of a other than 0, a to the 0 is equal to 1. We've shown that by this thing that we've just derived of a to the m divided by a to the n equaling a to the m minus n. So we also defined another thing. We defined that a to the negative n is equal to 1 divided by a to the n. This also we used when we were considering this thing right here. In fact, we can even kind of see it. If you consider a to the m divided by a to the n is m minus n, then a to the n divided by a to the m would be a to the n minus m, which is a to the negative m minus n. So we can clearly see inverting these changes or flips the sign of their index. We can see a to the n minus m is a to the negative m minus n. So clearly that's visible. I hope there's no confusion there, and let's carry on. I should mention, by the way, most of these during your paper solvings or whatever will be considered as obvious facts, and you will not be expected to state them in any way. Just write them and continue with your solution. You will not be expected to prove or state any of these index laws. You will simply be expected to quickly write them and use them to simplify or solve your problems. Right, let's carry on to the next thing, which is that what we have to consider when we have a to the m itself raised to the power of n. where m and n, for now, for our simple understanding, we will consider to be positive integers inclusive of 0, but do not have to be positive integers inclusive of 0. They can be any real numbers, and this will still work. So here, what a to the m whole thing to the power of m n means is that we have a to the m multiplied by itself, a to the m multiplied by itself, a total of n times. Each of these a to the m's is a times a times a dot 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 in total m times. So we have m a's here, and what we are considering is n sets of those m number of a's all multiplied together. So what we are considering as a to the m to the n is a times a dot 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 times a m times this thing being multiplied by itself, a times dot 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 times a. Here also m times, such like this, all of these brackets like this. I'm going to write this is just a times dot 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 m times. These brackets are each being multiplied by each other n times. So we have in total m number of a's being multiplied by themselves n number of times. So in total, if we count the number of a's that we have a times a dot 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 multiplying a lot of a's together. We have a total of m times n number of a's that are being multiplied together when we have a to the m brackets to the power of n. So we have a name for this. When we have a certain number of a's multiplied by themselves over and over again, we can write this in exponential form or indexed form. So here what we have is actually a to the this number. So we have a to the mn. And thus we can conclude that a to the m to the power of n is equal to a to the mn. This is of course equal to a to the n to the power of m. Can you see what I did there? I just swapped these two. Swapping these two or simply writing them as a product does nothing. It's the same exact value. So a to the m to the power of n is equal to a to the mn is equal to a to the n to the power of m. We're going to write this as another thing. This is true, and this is an index rule. You can use this thing when you're solving your problems. You can very quickly just multiply the two powers together. Let's say we have, for example, 3 squared cubed. This is 3 to the power of 3 times 2, so 3 to the power of 6. It's also equal to 3 cubed squared. So you can rearrange these things as however you want. You don't need to explain how you rearranged it. All of these index rules are generally taken as known things and are only there for you to apply them. No need to state them or prove them. Furthermore, another thing that's important to us is what a times b to the power of m is. A times b to the power of m is essentially multiplying ab by itself dot 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 ab times ab by itself m number of times. Considering this thing, we have a times b times a times b times a times b, and we have m number of these groups. So that means we have a certain number of a's being multiplied together. We can consider something like that. And then that being multiplied by a certain number of b's. We can extract this due to the commutative properties of multiplication. So we have times b times b. So what we have here, how many a's do we have? Well, considering we had m number of pairs of a and b's, we had m number of a's here, and we also had m number of b's here. And now we have repeated multiplication of something certain number of times, which we can of course rewrite in a different format. A being multiplied by itself together m number of times is a to the m, and b being multiplied by itself m number of times is b to the m. So we have ab to the m being equal to a to the m, b to the m. This allows you to break a product into its factors and write that in indexed form. As an example, we'll write this as a main point. I'm going to put a black thing around it to show that it's important. if we take, let's say, 12 squared, if you don't know how to figure out 12 squared, 12 is just 3 times 4. So we can write 3 times 4 and that thing squared. Now we can break this down into 3 squared times 4 squared. 3 squared we know is 9 times 4 squared we know is 16. If you multiply those together, you can get 90 plus another 54. 90 plus 54 is 144. I don't know what kind of use case you would have for this thing, but of course you can definitely find some kind of use case, and if you find that use case while you're doing the paper, you can of course directly apply it. No one expects you to prove this, it is a known thing. So that is when you have a times b to the power of m. Similarly, we can have a divided by b to the power of m. If we consider a divided by b to the power of m, what we have here is a times dot 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 lot of a's times a, whereas m number of a's here, we're dividing this thing by b times dot 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 bunch of b's times b. Here there's also m number of b's here. So we have m number of a's on top and m number of b's on bottom. So m number of a's, we have a meaning for that, we have a symbol for that. If we have m number of a's multiplied by themselves, that's just a to the m. Divide by, we have m number of b's multiplied together, that's just b to the m. So we can expand a fraction like this as well. You can say a divided by b to the m is equal to a to the m divided by b to the m. Again, there you can of course find some kind of use case for this. It depends on the question. While you're doing the question, you might notice, oh look, this looks like this pattern, and if I convert this into this format, I can see there's some nice cancellation happening or something like that. I don't know. We have to decide where to use these things, but you do not need to prove them or state them while using them. You can just use them. So here there's another condition: b should not be 0, of course, because if b is 0, we have divided by 0 on the left and right, which constitutes an issue. So avoiding that, this relationship is also valid. So that's that for this section. There's next part where we have to talk about fractional powers, i.e. roots, which we will get to right now. Now let's go on to what roots are. So a root is defined something like this. Let's say a and b are elements of the real numbers. If b to the power of n is equal to a, and let's also put that a is an element of, for now, the positive integers. Again, similar to how we started above with indexes of positive integers and expanded them to non-positive integers as well. Similarly, we will try and expand starting from n being a positive integer. So here, if b to the n is equal to a, then b is an nth root of a. b is an nth root of a. So this is what we mean when we consider a root. For example, the square root of 2 is the square root of 2 because the square root of 2 squared is equal to 2. Here of course there's another thing. Instead of second root or 2th root or some other thing, we say the square root, and the third root we say cubic root or cube root, and we do not say the third root. Sometimes I've heard people say third root, but just know square root, you should know this of course, I'm just saying it. Square root is second root and cube root is third root. Other than that, the rest of them are usually referred to by their numbers. For example, 4th root, 5th root, 6th root, and so on. We don't say like quartic root or quintic root or hexic root or some that kind of thing. Yes. We do not say that kind of thing. Usually, for powers higher than second power and third power, we say that n number powerth root, like 4th root or 5th root. So here, what we mean by the square root of 2 is that the square root of 2 to the power of 2 is equal to 2. What we mean by the square root of 3 is that the square root of 3 to the power of 2 is equal to 3. What we mean by the cube root of, let's say, cube root of 8 is that the cube root of 8 cubed is equal to 8. So here I want to introduce another notation. When we're writing roots, the square root does not have any number here. It's just written like with this symbol, and you put some number in the inside. For any higher root, any higher nth root, we put an n here. You would not be wrong in putting a 2 here to say square root, but it's not convention. If you just write the square root symbol like this on its own, it is implying the second root. If you want some other index for the root, like third root, fourth root, fifth root, then you need to put that into here. So here I have put a third root of 8. Now this can be confusing also, so when you're writing, make sure that this 3 is smaller than your normal 3, because here 3 times root 8, what I mean by this is that it is 3 times whatever the square root of 8 is. But if I write something like this, what this means is this is the cube root of 8. This is the number such that the cube root of 8 cubed is equal to 8. So note the difference. Here sometimes this can look confusing, so I encourage you, kindly make, when you're writing cube roots or fourth roots or higher order roots, make that number look much smaller so that you don't get it confused like this. Here this is 3 times the square root of 8. Here this is the cube root of 8. So please do that. And now with that, let's carry on and try to figure out what these roots are. So now circling back to the square root and nth other roots, when we have b to the n equal to a, it means that b is equal to the nth root of a. So let's try to analyze what this means. We can actually write nth roots in terms of indexes, and I'll show you how by analyzing these two equations. So here in the second equation, let's say that the nth root of a is actually a to the x for some x that we don't know. In that case, what we have is b is equal to a to the x, and we don't know what the x is, we just know that that's the case. Let's multiply both sides by themselves n number of times. So that what I mean by that is, let's consider b times b times b dot times b n number of times, and that would of course be equal to a to the x multiplied by itself n number of times dot times a to the x, a total of n number of times. So multiplying by something by itself n number of times is the same as taking that corresponding indexed power. So we have b to the n on the left, and we have a to the x whole thing to the n on the right. Now consider this equation here and this equation here. One of them says that b to the n is a to the x to the n. Other one says that b to the n is a. So therefore, a to the x to the n is equal to a, which is also the same as a to the 1, because a is a multiplied by itself one number of times. Now here, using our previously found knowledge of index rules, we can write a to the x whole thing to the power of n is simply a to the power of xn. So therefore, a to the power of xn is equal to a to the 1. If the left hand and right hand are equal, we can see that xn must be equal to 1, which means that x is now equal to 1 divided by n. So we have a different meaning for when we write the square root or any other nth root. The nth root, or what we write as this root of n of a, nth root of a, is the same exact meaning as a to the power of x, which is 1 divided by n. So note, if we have the square root of 2, this is exactly the same as 2 to the 1 divided by 2. If we have, let's say, the cube root of 9, is the same as 9 to the power of 1/3. If we have 27 to the 5th root, it's the same as writing 27 to the 1/5, and so on. So this is what we have here. This is now a new understanding of what an nth root really is based on indexes. An nth root based on indexes is actually the 1 divided by nth power of that corresponding number. You'll notice now, because n was an integer, we have now a non-integer, of course, provided that n is not equal to 1, we have now a non-integer up here. So this gives us that we can now express and understand what non-integer or fractional, or as we say in our set theory, rational number powers of A are. We can now express a rational number power of n, and we can say A to the 1 over n is simply the nth root of A. So A to the m divided by n is A to the 1 divided by n to the power of m, meaning that we now have the nth root of A to the power of m. So now we can express rational number powers in terms of these ideas instead of just integer powers. We have expanded our horizons of what indexes are. So here we can write this thing as our own new identity. Perhaps we can say that the nth root of A raised to the power of m is what we mean when we say A to the m divided by n. Similarly, from our index rules, we also know that A to the m divided by n, or A to the m times 1 divided by n can also be written as A to the m to the power of 1 divided by n, and we now know what power of 1 divided by n means. So therefore this is also equivalent to the nth root of A to the m. So you can see another interesting thing that just happened there. We have that the nth root of A to the m is equal to the nth root of A to the m. So we have just discovered another interesting thing. When we have indexes, we can take them inside or outside of our square roots, our nth roots. Here we can see root n of A to the m and root n of A to the m are both the same exact thing. We can take this index inside or outside of the square root without any problem. So here I'm going to label this thing because it's an interesting rule. I'm going to label it as a new index rule. This is an index rule. Also, this previous thing that we discovered where we have the nth root being equal to A to the 1 divided by n, I'm going to label that as well as an interesting rule. So here, now that we've broadened our horizon of what exactly the nth power really means, because now we have indexes that are no longer just limited to the integers. Now we have indexes that are rational numbers, not just integers. We have expanded our horizon on what indexes are. So we still have more to discuss, however. We are not done. We have now understood what roots are. Root is just the number that we have to multiply it by itself certain number of times in order to get a certain value. And we have shown that when we have indexes and roots, we can move the indexes in and out of the roots. There are a couple more identities that we can have here. We can have that the nth root of the mth root of A is equal to the mth root of the nth root of A. This is the same exact thing as writing that the 1 divided by nth power of A to the 1 divided by m is equal to A to the 1 divided by n to the 1 divided by m. This of course is true from our previous index law. Recall that A to the m to the n was equal to A to the mn was also equal to A to the n to the m. In the same exact way, what we have here is just the other 1 divided by version of that same thing. Here these are both actually equal to A to the 1 divided by nm. So we can write another thing here. We can also equate this to the nmth root of A. So here, giving a simple example, we'll put a box around this first. We'll put a box around this saying that this is a useful index rule. This is the equivalent of saying, let's say, given some example, if we have the square root of the cube root of 6, for example, this is the same as the cube root of the square root of 6. Now here I did put this 2 here additionally. It's not exactly required. I'm writing it here just so that you can clearly see what's happening here. So the square root of the cube root of 6 is equal to the cube root of the square root of 6. It is also equal to the 3 times 2 or 6th root of 6. So here is a practical example of this thing. We can clearly see this is the case. So we can use this, I don't know exactly where you would use this, perhaps with something like, let's say, the 8th root of 256 for example. The 8th root of 256 can be written as the 4th root of the square root of 256. The square root of 256 is 16 because 16 times 16 is 256. So we have the 4th root of 16. And then the 4th root of 16 is just 2 because 2 times 2 times 2 times 2 is equal to 16. So I don't know, you could potentially use it in this format. Generally in the papers you're probably not going to have this thing, or if you have it, you'll have it in some equation format. But this is an index rule, it is valid, so therefore it gets to be in its own box. If we have the nth root of a and we multiply it by the nth root of b, this is equivalent to the nth root of ab. This is exactly the same as the previous thing that we discovered, and we can write that in the same way. If we write this root thing in terms of 1 divided by powers, we have a to the 1 divided by n times b to the 1 divided by n, and it should be clearly obvious that this is exactly equal to ab to the 1 divided by n. From our previous index law, a to the n times b to the n is ab to the n. So here, there's nothing really new that we're discovering here. We're just rewriting this thing in terms of the roots so that you have a clear understanding that it's the exact same thing that's happening here. Similar to our indexes, when we have the rational indexes and roots, we still have the same index rules applying. So there. Similarly, if we have the nth root of a divided by the nth root of b, this is equal to the nth root of a divided by b. This is the exact same as a to the m divided by b to the m being equal to a divided by b whole thing to the power of m. Same exact thing, it's just expressed in different format. I will give it the liberty of writing it as a theorem, but it is really the exact same as the previous index rule that we discovered. Only thing is that instead of the indexes, we are replacing it with the root symbols. And perhaps one more honorable mention. If we have the nth root of a and we multiply it by the mth root of a, what we end up with is is, if we just write this in index format, 1 divided by n, a to the 1 divided by n, times a to the 1 divided by m, which is a to the 1 divided by n plus 1 divided by m, which is a to the m plus n divided by mn. So here the divide by mn part indicates that we have the mnth root of this thing, and then the numerator having m plus n means that the m plus m power is what we have here. So we actually have here the mnth root of a to the power of m plus n. So that means the nth root of a times the mth root of a is equal to this. So I added this as an honorable mention because someone might get this wrong. And write simply that the nth root of a times the mth root of a is equal to the mnth root of a. Not the case, it's wrong. Alright. So one of my friends actually tripped up with this and sent me his solution where he had made this mistake. So I'm just wondering if other people might make this mistake, which is why I pointed this out. So there. Now we have only a few other things to talk about in terms of roots before we can finally get to logarithms. It is that if n is even, then what we have is that the nth root of a to the n would be the absolute value of a. However, if n is odd, in this case, the nth root of the a to the n will be just a. So here, what's happening here is a little sign preservation. When you take any number to an even power, it destroys the sign, and when you have any number and you take it to an odd power, it preserves the sign. For example, negative 2 squared is negative 2 times negative 2. Negative 2 times negative 2 is negative 1 times negative 1 times 2 times 2. Negative 1 times negative 1 gives us 1, and 2 times 2 gives us 4, meaning we get 4 here. Similarly, 2 squared of course is 4. So here, if you take the square root of negative 2 squared, you get the square root of, we need to do the inside first. The inside is negative 2 squared, which is 4, which is then 2. So here we can clearly see the square root of negative 2 squared is going to give us the absolute value of negative 2, or simply 2. However, when you cube a number, for example negative 2 cubed, negative 2 cubed is negative 2 times negative 2 times negative 2, negative 2 times negative 2 times negative 2. These two will give us 4, negative 2 times 4 will give us negative 8. So because of this, the sign is preserved. Similarly, when taking the roots, the sign will be preserved with odd numbered roots, the sign will be destroyed with even numbered roots. Therefore, we have the property that the square root, or the nth root of a to the n is going to be the absolute value of a, given that n is even, and the nth root of a to the n is going to be a if the root is odd. So cube roots and let's say fifth roots and all of that will give you the same number on the out. However, square roots and fourth power roots and all of that will give you the absolute value of the value that you put into it. The fourth root of, let's say, negative 2 to the fourth is going to give you 2. It's going to destroy the sign. Alright, so now that's out of the way, let's go on to logarithms. Logarithms are a re-representation of the index abilities. If we say that a to the b is some number n, saying it like this, representing it like this, representing it in terms of an index and some base raised to some index, means that we can also write the same exact thing as log base a of n equaling b. If the left is true in this format, the right is true in this format. However, there are some limitations to this. We have the limitation that a should not be equal to 1, a should be greater than 0, and n should be greater than 0. This is limited. I'll explain why it's limited and why we want to keep it in this limited fashion, and why we need a to not be 1, because that might seem to you like a little bit of an odd choice here. Why cannot a be 1? So let's go into that. So here you have to first understand that the equation on the left is exactly identical to equation on the right. Writing a to the b is equal to n is identical to writing log base a of n is equal to b. Both are representing the same exact idea. So in this case, if a is 1, we have 1 to the b equals n. So for any b, for any finite b, 1 to the b is equal to 1, because multiplying the identity or 1 by itself any number of times is going to still leave you with just 1. So because of that, if n is anything else other than 1, we cannot find what the logarithm is. We cannot find any b such that 1 to the b is something that's not equal to 1. For example, 1 to the b equals 2. If you are asked to solve this equation, your answer should be, I cannot solve this equation. There is no b that I can put into this thing such that the left side is equal to the right side. So in the same way that this expression is unsolvable, because we can convert this into the other format, we can convert this into log base, and in this case the base is 1, so base 1, and here in this case n is 2, so 2 equal to b. So because the left hand side has no solutions, the right hand side also has no solutions. The logarithm base 1 is undefined because any power of 1 is going to be 1. There's no b we can find such that 1 to the b not equal to 1. Well, within the finite b that we are limited to, we cannot find 1 to the b being not equal to 1. So for that reason, we have that a should not be 1. Why cannot a be negative? Why should a be positive? Well, again, very similar reason. A cannot be 0 here. We'll isolate this thing. A greater than 0 means that a not equal to 0 and a not less than 0. So we'll examine the first case. If a is 0, we run into the same issue. 0 to any b is equal to 0 provided that b not equal to 0. Why did I say provided that b not equal to 0? Well, because if b is 0, recall, we have 0 to the power of 0. Within the same video, a little bit while earlier, I told you why 0 to the power of 0 is currently undefined. However, in most circumstances, we would take it as 1. There are some circumstances where you could take 0 to 0 as being equal to 1. So, because of that issue, a should not be 0. How about the other one? Why cannot a be negative? Well, let's try to think about this. Negative 2 squared is equal to 4. This is alright. So that means the log base negative 2 of 4 is equal to 2. All well and good, right? This seems like it works. It seems like there's nothing wrong here. So swapping the variables around, we have nothing wrong here. And you're kind of right, but also kind of wrong, because this is not the only solution. There are other solutions. We are not going to get into that. But now I'm going to introduce you into a problem. Let's say instead of 2 squared, I want 2 to the half power. What is 2 to the half power? Well, recall, 1 divided by n power is the same as the nth root. So here what I'm looking for is the square root of negative 2. Notice there's a negative on the inside. Recall that when you take the square root of a negative number, it becomes an imaginary number. It becomes I. So it's now within the complex numbers. Because of this reason, and to avoid this from happening, we try and make sure that the base we are using is not less than 0. It is not a negative number. If it is a negative number, there are certain cases where we can still get alright solutions. But there are some cases which we cannot get alright solutions. We will get complex solutions. Due to that issue, to avoid that from happening, to avoid imaginary numbers from happening, we say that a is going to be not less than 0. So this means that a is not equal to 0 and not less than 0, which means that a is greater than 0. And now n. Why is n limited to positive numbers? Well, we have a to the b, where b is a real number, b element of the real numbers. If we have a positive number to the power of anything which is a real number, we are going to get a positive number. We have to get a positive number out. And because the only way we can get 0 out of this thing is by doing 0 to some b, and we have already eliminated 0 as being part of our possible solutions. Oh, not there, sorry, here. Here we have eliminated 0 as being part of the solutions for a, which then means that we cannot have this n also being 0. So n is also not 0. N is non-zero, and because we have a positive number to the real power, it should also give us a positive number, meaning that n should also be a positive number. And thus, we have the limitations that a is not 0, sorry, a is not 1, a is also not 0 of course, a is not 1, a is a positive number, and n is a positive number. Within these limitations, for a, b, and n within the real numbers, this relationship is valid. So here, the relationship we have is a to the b equal to n if and only if we have that log base a of n equal to b. So it's important for you to understand that logarithms are just a rephrasal of the same exact thing. We are rewriting this format in a different way. This is the exact same equation here and here, just that it's been written in logarithm form compared to exponential form. So here, the only real important thing to try to understand is that the corresponding terms are still there. This is the base. On the left hand side is the base, and here this is the base. You'll notice when I read this I said log base a. That's because this right here is the base. Similarly, this is the index here. This is the index here. Index is also the answer on this side. We are carrying through the same exact equation, but we're just writing in a different format. So on the left hand side, what the question we're asking is, a when raised to the power b is equal to what? That's the question we're asking. On the right hand side, where the way we phrased it, it seems like we're looking for, I have a, I raised it to some power and I got n. What is that power? So these two are solving for two different things. If you tell me what's 3 to the 2, I'll tell you that you want me to find out 3 times itself 2 times is equal to what? In which case I'll write 9. But if you ask me log base 3 of 9, the question you're asking me is, what power do I have to raise 3 to in order to get 9? So I hope you understand it's the same exact expression. It's just that we are rephrasing it to ask a different question. So now that we understand logarithms and what they are, let's go through some logarithm identities which are actually derived from the index identities that we found earlier. So let's go. The first logarithm identity we have is that log base a of, let's say, pq is equal to log base a of p plus log base a of q. This is one of the main reasons why we like logarithms so much and we use them to do calculations. It's because they can turn multiplication problems into just addition problems. This is the main advantage of logarithms. It's why they are so useful. So we can prove this. I'll write it in a box as a known thing, but we'll prove it as well. But I'm not going to actually we'll leave the proof as well. So we'll leave the proof as well. Let's say let logarithm base a of pq be equal to n. What does this imply? Actually, I'll put a symbol in here. This implies from our relationship, because remember, saying log base a of pq equal to n is the exact same thing as saying a to the n is equal to pq. It's the exact same idea. So exact same, I'm going to write the if and only if sign here, exact same as saying a to the n is equal to pq. So now here, we'll suppose that p is equal to a to the r for some r, which we don't know. Let's also suppose that q is equal to a to the s for some s. Let's suppose that. It has to be true, no? It has to be true, because this right here is a positive number, and this right here is a positive number, positive number. It has to be positive number over here, because we had these conditions being matching. And recall from above, these conditions had to match. We had to have that a is a positive number and n is a positive number. So that means both of these are positive, which means it will work. So now given that, suppose that p is a to the r and q is a to the s. This has to be true for some r and s, which we don't know, but we don't need to know. We just need to understand that there exists some r and s for which this is valid. So in this case, p times q is what? pq is a to the r times a to the s, which is a to the r plus s. We all agree on that, right? Okay, it's correct. So then, from this equation, which I'll label 1 real quick, and this equation, which I'll label 2 real quick, we can see that a to the n is equal to a to the r plus s, which means that n is equal to r plus s. So what are n, r and s? Well, we already have that n is equal to log base a of pq. From these two equations, which I'll quickly write on the side, p equals a to the r implies the format that r is equal to log base a of p. I hope you can all agree on this. For this is literally how we define the logarithm. We define the logarithm such that if a to the b is equal to n, then log base a of n is equal to b. We are rewriting that using that format. P is equal to a to the r, which means log base a of p is equal to r. Similarly, if q is equal to a to the s, then we can say that s is equal to, I'll write the if and only if sign as well, s is equal to log base a of q. So substituting these 3 into here, right? If we write this thing here, this is 3, this is 4. Substituting all of these into here, we can see on the left hand side what we have is log base a of pq. It is equal to, and on the right hand side we have r, which is log base a of p, plus s, which is log base a of q. So therefore, hence proven, log base a of a product pq is equal to log base a of p plus log base a of q, provided that p and q satisfy, and a of course, p, q and a satisfy the conditions required for us to have a logarithm to be valid. Recall the logarithm valid laws. If a logarithm is valid, then a is non-1, a is greater than 0, and n is greater than 0. In this case, that means that all of these numbers which we have in here, which are pq, p and q, all need to be positive. So in this case, if p and q are already positive, then pq is obviously positive, so we don't even need to check that. So what we need for this thing to be valid is that a needs to not be 0, sorry, not be 1, it needs to not be 0 as well, but we write that as greater than 0, and p needs to be greater than 0, and q needs to be greater than 0. Given all of these conditions, then this expression here is valid. We can turn log base a of pq into log base a of p plus log base a of q. There's another thing that we can do. In a similar fashion to what we just did here, we can also say that log base a of p divided by q is equal to log base a of p minus log base a of q. This is also valid, and this is also stemming from a similar idea. We can actually directly get to this using the fact that dividing by q is the same as multiplying by 1 over q, and 1 over q is equal to q to the negative 1. So then you can kind of see it already, but we'll go through it and simplify and show you that it's true. Let's just do that real quick. So suppose again, we're going to do it again. Suppose that log base a of p divided by q is equal to n. What this means that a to the n is equal to p divided by q. So then let p equal a to the s for some s, and q equal, sorry, actually I wanted to put r for the first one, p a to the r for some r, and q equal a to the s for some s. In this case, what we have is that a to the n is equal to a to the r divided by a to the s. Recall that a to the r divided by a to the s, one power divided by another power, is equal to a to the r minus s. We can already see from this where this is going. This means that n is equal to r minus s. And now substituting the three values, n is equal to log base a of p divided by q, and r from this thing, r is equal to log base a of p, and then minus, and s is equal to log base a of q. So there we have it. P divided by q becomes log base a of p minus log base a of q. So again, this is why we like logarithms. It makes multiplication and division into addition and subtraction. It becomes much easier for us to do calculations due to this property. Moving forward, we can also have some other interesting things, like for example the fact that log base a of b to the n is equal to n times the log base a of p. You want to prove this one? Let's do it. So here on the left hand side we have b to the n. B to the n is equal to b times b times b dot 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 times b, total of n times. We've already just discovered that a log of a product is equal to the sum of each of the individual logs. Taking the logarithm of both sides, the logarithm base a of b to the n is equal to the logarithm base a of all of this, b times dot 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 all the b's times b all the way down. So here on the right hand side we have a logarithm of a product. We already know the logarithm of a product is the sum of the logarithm of each of the individual components. So therefore what we have here is in fact log base a of b plus log base a of b plus dot dot dot. How many log base a of b's do we have in here? Well, we had n number of b's initially, which means when we break it down, we should have n number of log base a of b's. So therefore, we have log base a of b to the n equal to n number of times of log base a of b. This is another handy little thing. We can take an index out of a logarithm. Logarithm of anything to a certain power is equal to the power times the logarithm of just the base itself. So in this case, we can write something like log base of 8 is log base 10 of 8 is log base 10 of 2 cubed is 3 times the log base 10 of 2. So here we can see that again it makes things simpler. Exponentiation now becomes simple multiplication when you deal with logarithms, which then makes our calculations much easier. I would like to take this moment to tell you a little something else also, something that you probably know from your O-level times, but I will mention anyway. The log base 10 is often just written as the log without adding the base 10, similar to how the square root is added without the 2, just writing the square root symbol. So here if you ever see just an empty log with no base, the base is base 10. And I should also tell you another thing. The log base e, where e is the exponential constant, is written as ln. We will get to that later and we will see it. I will explain it then as well. But for now, just know that there is some special number e, and when you take the log base e, we write it as the natural logarithm or log natural, which is written as ln. So just know that that's a little extra trivia fact, and we will get to it and explain it at that given time. For now, we have a couple more log rules which we need to discuss, one of which is that considering log base a of b and log base b of a, log base a of b is equal to 1 over log base b of a. This is also another one. I'm going to put a box around it and put a star. Let's quickly prove this one. So, to prove this one, we're just going to use the rules that we have established so far. Suppose that log base a of b equal to n. We just say suppose. So what this means is that, considering the form of the logarithm, a to the n is equal to b. I think we can all agree this is the case. A to the n is equal to b. So then, from this, let's consider what b is in terms of a. Well, if we take the 1 over nth power of both sides, we get a to the n to the power of 1 over n is equal to b to the 1 over n, taking the 1 over n power of both sides. On the left hand side, we just have a, because a to the n to the 1 over n is just a to the n times 1 over n, which is just 1. So a to the 1, which is a. So a is equal to b over b to the power of 1 over n. Taking the logarithm base b of both sides in this case, what we get, converting this into logarithm form, is that log base b of a is now 1 over n. I think we can agree on this. This is all correct. And now, finally, as a final step, comparing the two, from this thing we can see that n is equal to 1 over log base a b of a, and then substituting this result back into here, what we can see is that the log base a of b is 1 over the log base b of a. So there you go. That's a nice little another identity which we can use wherever we want, wherever valid, in order to either probably it might cancel something with something, or maybe make the equation simpler, so you can remember this thing and use it where necessary. Another handy one is that the log base a of b is equal to the log base c of b divided by the log base c of a, provided a, b and c are valid numbers to substitute into this log equation. We can prove this one easily as well. if we just rewrite the first thing as some value, right? If we write log base a of b equal to some n, what this implies is that a to the n is equal to b. Taking the logarithm of some other value on the both sides, we get log base c of a to the n is equal to log base c of b for some valid c. Now, on the left hand side, using the identity we found a while back, that a to the n powers logarithm will be n times the logarithm of that value, we can write the left hand side as n times the logarithm base c of a, and this is equal to logarithm base c of b for some valid c. So now finally we can see that n is equal to log base c of b divided by log base c of a. Hence, equating these two sides to each other, we get that the log base a of b is equal to the log base c of b divided by the log base c of a. This one also could potentially be useful to you in some times. So therefore, we're going to put a box around this one also and write it as a known function, as a known relationship, and you can use this relationship whenever you want, wherever valid. And that concludes this lesson. These are all the logarithm rules we have so far. Let's summarize them and end this lesson here. So going to the very top of our learnings today, we discussed what indices and logarithms are, starting with indices. So if you have a to the power of b is equal to c, a here is what we call the base and b here is what we call the index. Given this format, we found some relationships that, considering a to the m, this is what a to the m is. It's a multiplied by itself m number of times for integer m's. We later moved away from integer m's, but for now, this was how we knew what indexes are. We proved from this that a to the power of m times a to the power of n is equal to a to the power of m plus n. Furthermore, dividing two by each other, we found that a to the power of m divided by a to the power of n is equal to a to the power of m minus n. We only proved this for integers, but it is true for all the numbers, all the valid numbers. Furthermore, we showed one possible thing. We showed that a to the 0 is equal to 1 provided that a itself is not equal to 0. Because if a itself is equal to 0, then what we have here in the calculation is a divide by 0 issue. We have a divide by 0, which means we cannot define that value as being a certain amount. So currently 0 to 0 is undefined. However, following the pattern, we can use 0 to 0 is equal to 1 in some certain situations to derive certain results. But for now, I'm going to tell you that 0 to 0 is undefined. Other than that, any other a to the 0th power is going to be equal to 1. Furthermore, we showed a simple identity that a to the negative n is equal to 1 divided by a to the n. That's just what it means. And then we showed if you have some a to the m and you take that thing to the power of n, it is equal to a to the power of m times n. And also you can flip the two. A to the power of m to the power of n is equal to a to the power of n to the power of m. And then we showed if you have ab, some two terms multiplied together taken to a certain power, it's equal to the first term being taken to the certain power times the second term being taken to a certain power. And this can be done for as many terms as you want, of course. If you have abc, it can be done for abc as well. No limitations here. Furthermore, we then discussed the division equivalent of this. A divided by b to the power of m is a to the power of m divided by b to the power of m. Here, of course, we have the condition that b not equal to 0 because again, we do not want to divide by 0. Then we discussed furthermore what a root is. We discussed that if b to the n is equal to a, then b is an nth root of a. We discussed that this is the format that we have it. If you have the certain square root, then that square root to its squared power is going to give us 2. In this case, root 2 squared is going to give us 2 because root 2 was the value such that root 2 to the power of 2 is equal to 2. Similarly, we had cube root of 8. Cube root of 8 is the value such that cube root of 8 to the power 3 is equal to 8. We talked about how the second and third roots have special names. The second root is called the square root, the third root is called the cube root, but the rest of them are usually referred to by just either fourth root, fifth root, and so on. And then I also gave you a little cautionary tale on how you should write this number here. This is 3 times root 8, but this is the cube root of 8. Write the number small so that it doesn't get confused as a normal number. And then after that we discuss some rules about the index, how taking the power of 1 divided by n is the same equivalent thing as taking the nth root of a certain number. That's what taking the nth root really means. In which case we expanded our understanding of indices further beyond just integers and into rational numbers as well. We discussed a couple other identities that we can find from this, like something like the nth root of a to the m is equal to the nth root of a to the power of m. We can interchange indices and roots. And we showed a couple other identities like this. And finally, this extra bonus identity over here, the identity that some people got wrong. Nth root of a times mth root of a is not mnth root of a, it is in fact mnth root of a to the power of m plus n. So be a little careful, do not write the wrong thing. This is the correct identity, the other identity is the incorrect one. Nth root of a times mth root of a is equal to mnth root of a to the power of m plus n. And then we discussed what happens when you take the root of a power. If you have the nth root of an nth power where n is even, you get the absolute value of that certain value on the inside. However, if n is odd, a to the nth root is going to give us back directly a. We also have this thing, logarithms, where if you have a to the power of b equal to n, it is equivalent to saying log base a of n is equal to b, provided that a, b and n are elements of the real numbers, a is not equal to 1, which we discussed why a should not be equal to 1, and a is greater than 0 and n is greater than 0. We discussed why each of these conditions are kept. It is so that we maintain our values within the real numbers, because if we don't, we will end up with complex numbers, and we really don't want to do that within this lesson. Furthermore, we discussed some logarithmic identities that are related to logarithms over here. Log base a of a product is equal to log base a of one of the values times the plus the log base a of the other value. We discussed how this turns a multiplication problem into an addition problem with logarithms. Similarly, we discussed its converse, where you have a subtraction, same as p times q is equal to log base of a of p plus log base a of q. Log base a of p divided by q is equal to log base a of p minus log base a of q. And we discussed a couple other identities, like having a power on the inside, log base a of b to the n is n times log base a of b. So here again, logarithms have made things simpler. We have turned an exponentiation question into a multiplication question. Over here we have another interesting identity. Log base a of b is equal to 1 over log base b of a. So if you ever want to flip the two things around, like for example, if you don't know log base 8 of 2, but you know log base 2 of 8, which is the power to which 2 has to be raised by to get 8, which is 3, then you can say that log base 8 of 2 is 1 divided by this thing, so that is 1 divided by 3. So there we go. That is an example use case of this identity here. And then we proved a couple others, like this one here. Log base a of b for some valid a and b is equal to log base c of b divided by log base c of a for some valid c. And note, this c can be anything. Because this c can be anything, we can have a lot more flexibility. Of course, c has to be a valid one, so c has to be greater than 0 and c not equal to 1. These conditions have to be there. Other than that, c can be any valid number. So that is the conclusion of this lesson. There are a couple other logarithmic identities and logarithmic rules, and a lot more to talk about within the complex numbers about logarithms and exponentials. But unfortunately, because we do not have that lesson covered yet, it is in grade 13, not grade 12, we cannot discuss that. So that will be where we have to conclude the lesson for today. Thank you for watching, and goodbye.